Good day, guys. This is a very quick introductory or a revision on complex numbers, complex algebra. These are some things that you already know, but I thought maybe it is good to do a bit of an introduction on complex numbers and revise on how you could do some complex calculations in different representations so that you will be comfortable when you work with AC quantities where we also use complex algebra quite a lot. So we'll change over to the screen capture mode and then explain using the short uh, document that I have made on complex numbers.
Okay, uh, so let's start. Uh, so as you know, if we define a complex number as x plus jy, then we call it a complex number if j is defined as j squared is equal to minus 1, and then we call the x as the real part and y as the imaginary part. And then this representation, which is x plus jy, is of a complex number is called a Cartesian form of representation, where x and y can be, later I'll show you, can be used as x and y coordinates of a xy plane, so that we can um, plot the uh, the particular complex number on xy plane. That's why we call it the Cartesian form. And alternatively, we also can go for what we call as the polar form of a complex number, because a complex number can be represented as from a vector or a line which has a magnitude and a direction. So that means r here represents the magnitude of the complex number, and theta is the uh, direction or the inclination to the real axis or the x-axis. So if we use this representation, then the relationship between the Cartesian form and the polar form, as you know, is r is equal to square root of x squared plus y squared, which is the magnitude, and theta is equal to tan inverse y over x. So both these representations, as I said before, can be mapped onto Cartesian plane for a simple xy plane, with x-axis representing the real part and y-axis representing the imaginary part. So then this is how it looks like. This is your complex number, this is your real part, this is your imaginary part, and this is your magnitude r, and this is your inclination to real axis. So as you can see, no matter if it is in Cartesian form or in polar form, it is possible to map it onto a complex plane graphically. Another form of representation of a complex number is using the Euler's formula. Now what is exponential, or e to the power j theta, where j is the j theta is a complex or an imaginary number. Then if we use the series expansion of e to the power x to expand this, then this is what you get: 1 plus j theta plus j theta squared divided by factorial 2 plus j theta cubed divided by factorial 3, and so on. And if we simplify all these powers, then we get any even power will eliminate j, because j squared is minus 1. Because of that, j theta squared will result in minus theta squared divided by factorial 2, and j theta to the power 4 will give us plus theta to the power 4 divided by factorial 4, and so on. And remember, the other one minus will be minus theta to the power 6 divided by factorial 6. So the real part, there will be a series of real terms, and then there will also be a series of imaginary terms because of the odd powers of j theta. So j theta will be there, and then we end up with minus j theta cubed divided by factorial 3, and the other one will be plus theta to the power 5 divided by factorial 5 minus etc. And then if you remember the Taylor series expansion of cos theta and sin theta, you will see that cos theta is equal to 1 plus theta square 1 minus theta square divided by factorial 2 plus theta to the power 4 divided by factorial 4 and so on. Similarly, sin theta will then be theta minus theta cube divided by factorial 3 plus theta to the power 5 divided by factorial 5 minus etc. So therefore, for these two, real part and imaginary part, we simply can substitute cos theta and sin theta, which results in e to the power j theta is equal to cos theta plus j sin theta. And this allows us to represent a complex number in exponential form as z is equal to re j theta, where this one splits into a real part called cos theta and an imaginary part of j sin theta multiplied by r gives us r cos theta as the real part plus j r sin theta as the imaginary part. And then going further down on complex addition and subtraction. Now in Cartesian form it is easy to add and subtract complex numbers because the real part and imaginary part are separate. Real parts can be added separately or subtracted separately. Imaginary parts can be added and subtracted separately. So z1 is equal to x1 plus jy1, z2 is equal to x2 plus jy2. So z is equal to z1 plus z2, and z1 is x1 plus jy1 plus x2 plus jy2. So x1 plus x2 are the two real parts, jy1 plus jy2 are the two imaginary parts, and then taking the j out, I can write x1 plus x2 plus jy1 plus y2. And in the subtraction, again z1 and z2 are defined like this, and then z will be z1 minus z2, x1 plus jy1 is z1 minus x2 plus jy2. So the two real parts subtract together and two imaginary parts subtracted together, giving us x1 minus x2 plus jy1 minus y2. And the same can be done in vector form. This is my x1, z1, this is my z2. So what is z1 plus z2? If you look in terms of the coordinates, what you have to do is to add x1 with x2. So to do that, what I do is I just project this z2 to the end of the vector z1 to give me this projected vector of z2, shifted vector of z2. Then you can clearly see that this projected tip will be x1 plus x2. Similarly, on the y-axis, this is jy1, and the projected vertical component of z2 will be coming from here up to here, which will give me finally jy1 plus y2. So if you think of a parallelogram with the two complex numbers representing two adjacent sides of that parallelogram, the diagonal of that will give you the addition of the two complex numbers. And subtraction, all you need to do is, if it is z1 minus z2, all you need to do is just flip z2, get the flipped version, which will give you minus z2. Alright, so once you have minus z2, then it is just a matter of adding z1 and minus z2 by doing the same geometrical construction that we did before. What is that? We just project this one from the to the tip of z1, which gives me this vector. So from start to the end of the two vectors is this diagonal, which is z1 minus z2. On the other hand, in fact, in magnitude and direction, you will see that it's the same as this diagonal, the other diagonal connecting the end tips of the two complex numbers. But it is always advisable to do the construction in this way, so that you wouldn't make any errors, mistakes in terms of the angle of the resulting complex number. So that is complex subtraction in vector form. How about multiplication and division? That is easily done if the complex numbers are in polar form. If it is in polar form, as you can see, it is like r1 angle theta 1 multiplied by r2 angle theta 2. So the two magnitudes are multiplied together, the two angles are added together. So we get r1 into r2 angle theta 1 plus theta 2. In division, you get the magnitude ratio and the difference in the angles. So r1 divided by r2 angle theta 1 minus theta 2. So I'll just show you only the multiplication in vector form. So if you have r theta 1 as your first complex number and r theta 2 as your second complex number, what happens is the two in the resulting vector complex number will have a length of r1 into r2 and an argument or an inclination to the real axis of theta 1 plus theta 2. So it is a vector rotation and an amplification in the magnitude. So that is multiplication in vector form. I'll not bother to show you the division in vector form. All you need to do is to get the ratio between the two magnitudes and angle difference and construct a vector. So it won't be this long in that case, and will be rotated the other way around a bit depending on the angle difference. So and then let us also look at multiplication in Cartesian form. It can be done. It's a bit cumbersome to do that. So all you need to do is substitute x1 plus jy1 multiplied by x2 plus jy2, and then multiply real part separately, x1 plus x2, and then as you can see the imaginary part separately, jy1 into jy2, plus there will be two other terms, cross multiplication, x1 into jy2, x1 into jy2, and then jy1 into x2. So now what happens is, where j squared comes in, it becomes a sign change, and you get x1 into x2 minus y1 into y2 as the real part. And then wherever opposite numbers multiply, like a real part and an imaginary part, product between real part and imaginary part results in an imaginary part. Therefore you get these two imaginary terms, j x1 into y2 plus y1 into x2. So that's the multiplication in Cartesian form. And then division in Cartesian form. How you do that? That again is a bit cumbersome, but can be done. So x1 plus jy1 divided by x2 plus jy2 is equal to, what you do is you have to get this part, convert this to a real number to do this simplification. So what we do is, as you may remember, we multiply from the complex conjugate of the complex number in the denominator. What is the complex conjugate? I'm talking about it soon. Like maybe I can revise that first. So if this is a complex number, x plus jy, complex conjugate of that is x plus jy written as conjugate, which is equal to x minus jy. In r theta form, it is simply change of the sign of the angle. And in exponential form, re j theta, conjugate is re minus j theta, which results in, there is a mistake, r cos theta minus rj sin theta. So I'll upload the correct version when I upload the PDF file of this one. So then going back here, what you do is multiply from the complex conjugate of x2 plus j by 2, which is x2 minus j by 2, x2 minus j by 2. So you multiply the numerator and the denominator so that you wouldn't make any difference in the ratio or the division. And then you do the find the product. So you multiply, resulting in 4 terms in the numerator and 4 terms in the denominator. But in the denominator, if you look at carefully, this one will give us plus y2 squared, x2 squared plus y2 squared, and you can clearly see that these 2 terms cancel out, resulting in a real number in the denominator. Now the rest is easy because you got x1 x2 plus y1 y2 divided by x2 squared plus y2 squared as your real part, and j y1 x2 plus x1 y2 divided by x2 squared plus y2 squared as your imaginary part. So that is how you do the division in Cartesian form, and then this is complex conjugate of a complex number, except for this little mistake. It has to be negative. So I'll do that correction, and that's it. I hope this will help you in memorizing all the complex mathematics that you have learned before. Thank you.